In this video, we're going to talk about several other random network models that can be used to build synthetic graphs. This is by no means an exhaustive list, and in some ways this list was created to show kind of one idea that various different models and various different configuration approaches can generate scale-free graphs. So that's kind of the consistent theme throughout many of the models that we'll see in this video. But again, there are many that do that as well, and many that reconstruct other important characteristics of graphs. So the first one we'll talk about is the Barabasi-Albert model. This takes in two parameters, one that is the number of nodes, one is this Q parameter. And this is essentially the number of edges that each node contributes to the graph. And we'll see exactly how that works. So the initialization step says that we start with a click of Q nodes. So that means Q nodes that are completely connected together. And then what we're going to do is we're going to add node by node. And we're going to call these kind of time steps. And we're going to index the nodes, the vertices V sub t, where t is the time at which they're introduced. And so at each time step, we're going to introduce this new node, and this new node is going to have Q connections. And so we're going to connect this new node, VT, with Q other of the existing nodes. And so clearly, only values of T that are smaller than this current value of T will be currently in the graph, and the other ones that are greater will then be not yet to be added. So that means we're going to be adding an edge between some VT and some VI, where I is less than T. And so this is the important part. This is what's called preferential attachment. And this is the idea that that we're not adding an edge. The probability of adding the edge between VT and VI is not uniform across the nodes. In fact, it goes with this probability, and this expresses the fact that it's going to be proportional to the degree of the node. And so it means that nodes with high degree will have then a greater chance to receive edges from new nodes. And so in particular, if a node has 3 times the degree of another node, it's 3 times more likely to receive an edge from a new node. And so this is this idea of the rich get richer. And so what the Barabasi-Albert model shows is that this idea of the rich get richer phenomenon is one way to generate a scale-free graph. And in particular, asymptotically, you can show that the degree distribution of the Barabasi-Albert graph goes with an alpha, essentially that slope in the log-log plot of 3. And so if you generate your graphs in the lab, you'll see that you don't quite get 3, but you should get something close to that if the number of nodes are large enough. Several BA properties that we can consider that can be proved, but we won't go through them, is the average shortest path. You can go back and compare this with the ER shortest path. It's relatively similar. One of the other important considerations is the clustering coefficient. Many real graphs exhibit some notion of clustering, but what we observe here is that as n gets bigger, the clustering coefficient decreases. And so that means that this network model does not generate an appreciable amount of clustering. There can be a directed version, and typically we denote the edge from the new node to the old node. So some new student is coming into a class, and based on the existing population, the popular ones are going to probabilistically get an edge. And so this edge would denote the new node, the new student, pointing friendship towards the old student or the existing student. There can be a number of other extensions that are interesting. In particular, you can change exactly how the preferential attachment calculation works. So it could be not necessarily linear, so it doesn't necessarily have to be just proportional to k. It's also possible that you could have preferential attachment based on some other characteristic other than degree. The next model we'll consider is called local attachment, and it takes in 3 parameters. the number of nodes, the same kind of Q parameter, and another parameter QR. And QR has to be less than Q. It's also greater than 0. And these are integers. And so this is inherently a directed graph. In this case, we start with something quite similar. It's a clique of Q plus 1 nodes. And again, we're going to add nodes step by step. And so at each time step, we introduce a new node, and the fraction QR, so not quite all of the edges, because all of the edges is going to be Q, but QR of the edges are added randomly, uniformly throughout the graph. So there's no preferential attachment here. We just uniformly add edges, QR of the edges that the new node has, to other nodes in the network. Then what we do is we look at neighbors of those nodes that we just recently connected to, and we add the rest of the nodes, so that's Q minus QR, those we're going to add uniformly to the neighbors of the nodes that we just connected to. And so this inherently has quite a bit of clustering in it. And so this is one of the modifications that that actually motivated Y to consider a local attachment model. One of the interesting things is that this can generate networks that are surprisingly similar to Barabasi-Albert methods, even though the mechanism is different. And so this is our first time to underscore the idea that for certain choices of parameters, we can get a scale-free degree distribution. Not for all parameters, but for some, we can get scale-free behavior. And so that means that this mechanism of random attachment plus local attachment is another way in which you can generate scale-free graphs. The third mechanism that we'll talk about is the vertex copying model, sometimes called the duplication divergence model. And so this takes in two parameters, n, the number of nodes, and a probability p, so that probability needs to be between 0 and 1. And so this begins with two connected nodes, just connected with each other. And then at each time step, we're going to select a node and duplicate it. And so by duplicating, it means that I create a copy of that and I maintain all its connections. And so that's the first step. And then what we do is we toss a coin with probability p to decide if we keep some of those edges. So for each edge that we had, that we copied, we're going to flip that coin to decide if we keep it or not. And if we end up discarding all of the edges that connect the graph, so this node is now disconnected, we delete it and we retry. But in general, there should be some edges left that somehow mimic what the copied node was like. And so this is a biologically inspired model that that generates some unusual degree distributions, but for some choices of parameters, you can also get scale-free degree distributions. And so this is another interesting example where we can create scale-free graphs using a completely different mechanism. Other than preferential attachment, other than local attachment, we can also do this duplication method, and that also generates graphs with scale-free behavior. Two other networks that are worth mentioning while we're talking about synthetic graphs. One is regular networks. These are actually quite common in a lot of engineering literature. For example, if you're talking about game theory concepts or communication, oftentimes they'll be on a quote-unquote network, but oftentimes these networks have very high structure associated with it. And so when we talk about regular networks, this is the idea that all the nodes have the same degree. And so oftentimes this is a realistic assumption, but it often doesn't model the nature that is in many real-world graphs. The last model that we'll consider is the small world network, and so you're going to see this in the lab as well. This takes in three parameters, n, q, and p. P is a probability, and the parameter q needs to be even. And so this kind of has a visual setup to it. What we do is we place all n nodes in a ring, and what we do is we connect nodes to its left and right by q over 2. So if q is 4 and we have nodes in a ring like this, then q is 4, then that means we're going to connect this node to the 4 nodes closest to it. So 2 on one side, 2 on the other. And then you would repeat this process for all of the nodes in the ring, which creates a structure of connectivity that essentially wraps around the network. And then what we do is we randomly uniformly, so this is exactly like ER, we're going to connect nodes with probability P. So then I take all possible pairs and I flip a coin with probability P to see whether or not we create essentially these chords that, that cut across the circle of the graph. And so the idea of this is that without these chords that cut across the graph, this circular ring does not exhibit the small world property, that essentially the bigger this gets, the longer it takes, the number of hops it takes to get around this network. But as soon as you introduce these cutting paths across the network, then that allows you to recover the short average paths that are characteristic for small world networks. So these are just a few random graph models, and there are many that exist in the literature, but understanding kind of how they're created and the motivation for them is what we're interested in this class.